our technical webinar on reservoir geochemistry, which is organized by the EAGE local chapter in Kuwait. It's a pleasure to have all of you here today joining us virtually to delve into the exciting realm of reservoir geochemistry and its crucial role in understanding subsurface hydrocarbon systems. So now I'm pleased to introduce our esteemed speaker, Dr. Placido Franco, a well-known geochemist at Geolog Technologies in Milan. Dr. Franco has an impressive educational background, holding a master's degree in organic geochemistry and PhD in analytical chemistry. This specialization lies in the application of organic geochemistry tools in various exploration, development, and production-related topics within the oil and gas industry. With his expertise, Dr. Franco has focused on conducting oil-to-oil and oil-to-source correlation, assessing reservoir continuity, studying fluid heterogeneity, addressing production allocation, and ensuring flow assurance. He is actively involved in the development of new lab methods and innovative analytical technologies for field deployment, particularly in the area of advanced surface logging. Dr. Franco's contribution extend beyond the lab and into the scientific community. He has co-authored several peer-reviewed papers and actively participated in several national and international scientific conferences. His research and insights have significantly advanced our understanding of reservoir geochemistry. Today, Dr. Franco will enlighten us on the role of reservoir geochemistry in supporting static and dynamic reservoir modeling. We are fortunate to have him share his knowledge and expertise with us. And now I would like to introduce Dr. Franco to begin his presentation. Dr. Franco, over to you, and the floor is yours now.
So, thank you very much for your kind introduction, your kind words. So thank you all for being here to this webinar. And once again, thanks to the EAGE local chapter in Kuwait for inviting me here and for having me here to talk about this topic, which I believe is particularly interesting, and which is about the use of reservoir geochemistry to support static and dynamic reservoir modeling topics. So, well, the topic is actually quite broad and diversified. So, having an extensive and in-depth discussion is basically impossible due to the limited amount of time that I have. That's why I will be quite general during this presentation. But still, I will try to give you some relevant information and show you some relevant applications. And to do so, I decided to break this presentation down to three main parts. So intro to the methodology and some application in static reservoir modeling and dynamic reservoir modeling. So since reservoir geochemistry is the main topic of this presentation, I would like to spend a few words about it first. So when it comes down to geochemistry, probably most of you are more familiar with concepts of geochemistry in exploration. So all the tools that geochemistry utilizes to better understand hydrocarbon generation, migration, and accumulation processes within a basin. Because, having just a structure is not enough to account for an oil accumulation. We also need to take into account all those factors controlling hydrocarbon generation until its accumulation, but also post-accumulation processes. And all of this is encompassed by the exploration geochemistry, which incorporates in the petroleum system modeling, which in turn integrate with the basin modeling. And all of this strongly decreases exploration risks. But this is mostly concerned with exploration. So when we move to development and production stages, geochemistry still has a lot to say. And all those applications in the development and production, so in reservoir engineering and production engineering issues, fall within the branch of geochemistry called reservoir geochemistry, which is definitely, younger than exploration geochemistry, but still has established a very good track record of successes and application. And today it's considered a very mature discipline. But let me take a step back before moving on. So, as I said, the reservoir geochemistry has been around for the last 30 years, I would say, something more, 30, 40 years. And first applications trace back to early 90s, where Mr. Robert Kaufman at Chevron basically used it to understand which was the leaking level in a subsea well. So they had this leak in the middle of the ocean, and they needed to understand where this leak was coming from. Since then, first applications were in to understand, production in some fields in Indonesia and in Gulf of Mexico. But since then, a lot of progresses have been made through improvements in analytical capabilities, but also data treatment capabilities. And this brought to enlarge the scope of work to understanding reservoir architecture, the fluid properties, understanding compositionally graded columns, understanding how, the different distribution of the fluid within the field, and moving to production allocation, production monitoring, flow assurance applications, and more recently this area is bloomed in the U.S. for what it comes down for what concerns unconventional plays and understanding rock drainage over time. The entire concept rotates around what is called geochemical fingerprinting. So when I have to explain geochemical fingerprinting, the best way, in my opinion, is try to compare it to human fingerprint. So similarly to the human fingerprints, which allow us to distinguish between people, petroleum is such a complex matrix. It contains thousands of compounds. So ideally, each oil sample is different, ideally, because, we should always be able to find some small molecular features that will allow us to differentiate oils. And that's exactly the concept of petroleum fingerprinting. And, this represents a huge resource that we have, be able to distinguish between oil samples at molecular level. And how we do that? Well, the idea that's behind is generally using gas chromatography related techniques. That's why petroleum fingerprinting is often called GC fingerprinting, because most of the fingerprinting applications rely on the use of GC, gas chromatography analysis. And the way we do that, well, actually, it's not important. The important thing is being able to obtain reproducible and consistent GC profiles, GC fingerprints of these oils. And the way we do that, as I said, is irrelevant. So some people, some laboratories use the original technique adopted by Kaufman, by Mr. Kaufman, so the high resolution GC analysis. Some other labs use, for example, target multidimensional GC analysis. Some other labs use untarget multidimensional GC analysis. Others use GCMS. So it doesn't matter as long as we get an in-depth analysis of the oil. Of course, after that, we need to process the data. And, in this case, we generally use, chemometric techniques such as PCA, principal component analysis, which helps us to reduce the tremendous, amount of data that we can draw out of a chromatogram. We can use cluster analysis to group different samples and make some correlations. And when it comes down to production allocation, we can also use dedicated unmixing algorithms to unmix a commingled signal. But I will talk about this later during this presentation. There's a multitude of reservoir geochemistry applications, and of course literature is particularly rich of examples. So I invite you to take a look at literature if you're interested in this topic, because it's very, very interesting. Anyway, I try to summarize in this slide those applications that I believe being the most relevant. In any case, I will not be able to talk about all of them because, due to time restrictions, I had to make some choices. But anyway, some literature references are cited here and there during the presentation. So if you think it's the case, you can start from there and investigate a little further. So let's start with a topic that I think is very important. So the first application I want to bring to your attention is the importance of fluid distribution and reservoir continuity in an oil field. And how can we use geochemistry to address it to some extent? So the field management is strongly dependent on the fluid distribution and the reservoir continuity, because this will define how to locate, for example, production injection wells, how to evaluate the quantity of producible oil, because the reservoir continuity, for example, it will tell us how many resources, how much resources we have access to. It will determine the field profitability. It's crucial to design enhanced oil recovery strategies and also to forecast production rates. So in general, a lot of mistakes have been made in the past because, for example, these aspects, fluid heterogeneity and reservoir compartmentalization have been under-evaluated. These have been aspects that have underestimated, overlooked aspects, and this caused huge failures in field management, in the field management, because actually the economics of the field was much lower than expected due to this unexpected compartmentalization. And this can hugely impact in the company value because it will impact on the field itself, in the field economics. So this is just an example that I taken from literature. Basically, Schlumberger just compared, as an example, these two fields, offshore fields in the North Sea. One of the fields was very highly connected, so very good reservoir connectivity. In the second one was a poorly connected reservoir in this offshore field. What it's clear is that in the highly connected reservoir, we have a steady increase in the oil reserves, while shortly in the poorly connected reservoir, shortly after production began, we had this strong drop in the oil reserves. And this was due to unexpected compartmentalization. So this is just to give an idea of how important this aspect is for field management. And, when it comes down to understanding reservoir connectivity and the distribution of the fluid in the reservoir, there are some information that we can use to gain some understanding. So, for example, we consider that we don't have compartmentalization, but when no block changes exist in the histological characteristics, or when we have seismic reflectors that are continuous, or fluids are in pressure equilibrium, or there's a common petroleum water contact, but also fluids have similar or continuous PVT properties of geochemical fingerprints. Anyway, if the biggest mistake that we could do is taking just one of these different points and basing all the interpretations and all our models just on one or two of these. Because, for example, faults might or might not have sealing properties, okay? Or for example, pressures in different reservoir compartments can equilibrate through a common aquifer. This doesn't mean that the oil column, the oil pool is, communicated. The oil pools are in communication, and this is a huge mistake that we can do if we rely just on pressure, for example. Or, variations in PVT and geochemical properties may result from complex petroleum accumulation history. So still, we consider that there is a compartmentalization because we have, a variation in the PVT features or petroleum fingerprints. Still, this may be just the result of an ongoing mixing process or multiple charges or ongoing biodegradation. Still, the fluid column is continuous. So, the idea is that the best way to success is trying to integrate as many tools as we can to decrease uncertainty. And when it comes down to reservoir geochemistry, well, this is particularly easy tool to integrate, and is particularly an expensive tool that I believe, we believe, the community believes that is definitely a shame not try to take into account in all prospects, in all place. Plus, a lot of operators and service companies implemented reservoir geochemistry tools and reservoir geochemistry capabilities. So nowadays it's pretty easy to have access to laboratory services aimed to this. So let me just give you an example of the importance and how we can use geochemistry in a simple and effective manner to address reservoir management aspects. So this is a case study that here in Geolog and in Geotech we carried out in India onshore in cooperation with the national oil company. We also published this work at the OMC in 2021, if I'm not wrong. So we are, as I said, onshore India. We are talking about the Bagyam field, and the reservoir is the Fatehgarh formation. So, well, overall, good porosity and decent permeability reservoir. We're talking about a medium gravity oil, so everything was fine. They put in production, but after some time they realized that oil production declined below expectations. Okay, and also they had the operator had a fast increase in the water cut, and they realized that this was due to a sharp increase in viscosity of the oil toward the oil water contact, and the increase in viscosity made the oil not movable. And this increase in viscosity was basically due to oil biodegradation. So, and they realized that, by taking a lot of samples, a lot of downhole samples and making viscosity measurements, to try to map the fluid heterogeneity across the field. But as taking all those samples, downhole is extremely expensive. So the challenge here was viscosity caused by biodegradation. So a physical cause, viscosity caused by a geochemical process, which is the biodegradation, and of course heterogeneity. They needed to describe it, okay? They needed to understand it in two different scenarios. While drilling for completion purposes, because they wanted to complete the well where the oil was movable, but also, map the oil quality and heterogeneity across the field. Okay, so that was the challenge. So the solution that we proposed was based entirely on geochemistry. So why don't we try to characterize fluid from the rock samples, in this case, core samples and cuttings samples, which were available from many wells across the field. And what tools did we use? So the idea was, well, if the biodegradation is the problem, can we describe biodegradation using geochemistry tools? Of course, the answer is yes, because biodegradation has been there's a scale of oil biodegradation, because these bacteria tend to remove the different components in the oil in a preferential way. So they like to eat some components first, and then when they run out of these components, which, for example, are the normal alkanes, they move to other classes, okay? So by following the variations of specific components in respect to others, we can monitor the biodegradation progress, the ongoing biodegradation. And in this case, the idea was, okay, why don't we monitor this ratio, for example, pristine over C17 or phytane over C18. And in this case, we used a portable instrument, the portable technology on site to describe oil quality while drilling or quasi real-time manner. Because during biodegradation, when biodegradation increases, this ratio, pristine over C17, increases, because bacteria tend to eat C70 first, and then biomarkers such as pristine or phytane. And when we move to a higher biodegradation level, we can also apply this concept by monitoring other compounds, other classes that are more resilient to biodegradation. So this is the basic idea that we used. And these are just the results. For example, as you can see, in this case, we are since we have mud contamination here, and we cannot monitor the pristine and fighting biomarkers, we are monitoring some other biomarkers, in particular C29 noropane and C30 opane. Okay, and as you can see here, these ratios are changing, going towards oil-water contact. So if we apply these tools on while drilling, we can basically understand when it's time to stop drilling, and complete the well, because we're gonna complete the well in the zone where we don't have the viscous oil. So this was how we addressed the first part. And the second part was addressed by doing some analysis at the laboratory level, collecting samples from all over the field and making some analysis at laboratory level. And as you can see, it was pretty easy. If we plot this particular ratio, C29 noropane versus C30, we have a profile, a curve like this one that is very, very similar, that mirrors the viscosity curve that I showed you before. But of course, in this case, the measurements are done on surface samples, so core chip samples, but also cutting samples. This is a very nice example of how we can use geochemistry to understand and to map oil quality across the field, and how we can use it to take ready decisions almost also while drilling. Another important aspect, which is very close to fluid distribution and fluid heterogeneity, is the reservoir compartmentalization. I mentioned that earlier, but let's get back to it. How can we define the reservoir compartmentalization? Well, reservoir compartmentalization is defined as the segregation of fluids within individual non-communicating compartments. Okay, so we can use reservoir geochemistry tools, petroleum fingerprinting, to better understand the hydraulic continuity of the oil in the reservoir. And this is all based on one premise and one assumption. So the premise is oils from a single reservoir have nearly identical fingerprints, while oils from separate reservoirs usually have subtle but consistent differences in their fingerprints. And we also assume that post-accumulation homogenization of hydrocarbon fluids after filling the trap is rapid. So if we assume this, if we take also, we consider true also the premise, the idea that's behind it, it's pretty simple. We take oil samples from the region, from the zones, from the layers, from the wells, whatever you need, that we want to test, and we compare them. So if we find differences, significant differences, well, those differences will, tell you that there's some chances we're talking about compartmentalized reservoirs. Otherwise, if it's the same fingerprint, well, we can go on the other direction, that maybe there's a continuity. Of course, all of this must be taken, it's not like a black box approach. It's not like a yes or no. We always have to put into the context, because as I said before, relying just on one evidence can bias a lot the interpretation and can lead to huge mistakes. So this is an example of how we used the mentioned approach in an offshore field in Gulf of Mexico. So basically, what we have two wells. Each well, we have two different layers. So the operator wanted to understand in well number one the vertical continuity between these two sand layers. They suspected being the same body, actually. And in sand number two, same thing. They wanted to understand the vertical compartmentalization between this body, sand 2, and this body, sand 3. But also, they wanted to understand the continuity between the sand 2 in well number 2 and the sand 1 in well number 1. And they also gave us, so they basically gave us oil samples from each layer, because they had all these layers tested. And they also gave us some oils from the same field but in a different area that they knew for sure being separated from the investigated one just to use it as QC. So this is just a recap of the results that we had. So if we look at this PCA plot, each analysis was carried out in triplicate because we want to understand the analytical repeatability, because the difference in the fingerprints between fluids has to be higher, of course, than the analytical repeatability. So what can we see here? Well, we can see that as expected, well, number one, the two levels actually fall within the same cluster. So here, as the expected, SEND1 is just a unique body in well number one. But also, they see that well number two, SEND3, and well number two, SEND2, well, they have pretty different fingerprint. The oils have pretty different fingerprints. They are different between each other, but also different from well one oil. So all of this brought us to hypothesize this this scenario here with just one whole sand body in well number one, laterally disconnected from this level in well number two, which is also compartmentalized in the underlying level that we call here sand number three. So how do we compare this data with other pressure data, for example, that they had? So once again, this is the schematics of the well. And what you can see here is that, well, number two well, SEND3, falls in a completely different pressure regimen, okay? But if we look at the well number one, SEND1, and well number two, SEND2 pressure profiles, well, it actually seems that, they fall within, the same pressure trend, okay? So if we only base our interpretation on this, well, we have one. It seems like there's no vertical compartment. Well, there is no lateral compartmentalization. If we base all our interpretation on this model here, it seems that there is a lateral compartmentalization. So two different results. Of course, this is important because the operator now has to better investigate and needs to understand which is the cause in between these changes. Could be anything. It could be like, for example, it's not uncommon to have, even though we have compartmentalization, it's not uncommon to have different, the same pressure profile still. Or on the other end, there might be some communication. Still, we have some process that causes variations in the fingerprint. So, but this is something that is telling that we have to be careful when we model our reservoir. So at the end of the day, as you can see, in this case, it was pretty easy to integrate the reservoir geochemistry approach into the existing data, because you just needed oil samples coming from each well to be checked. This study was pretty fast. It took more or less 2 weeks. And we always suggest to try to integrate this kind of studies in the model. Of course, The limitation of the study are pretty obvious. We need the oil samples from the different levels, or at least we need oil samples from wells that we think being connected to the ones we want to test, or where we think that the oil is actually representative of the target one. Still, we can do some assumptions, we can do some approximations, but the biggest limitation is that we actually need oil samples from intervals to check. And of course, if we have strongly accurate oils, this is not the best situation to deploy this technique. So now I will move to the last part of the presentation, when I'm gonna talk about some applications in the production. So most of the things that I showed you concern, static reservoir modeling. But what happens when we put everything in production? Well, when we put everything in production, a common practice in the oil industry is to perform what is called oil commingling. So this is done for many reasons, economic reasons and practical reasons, most of all. So separate hydrocarbon flows are commingled in single points and then exported. But and there is a huge need, to know how much oil, is coming from one pool and how much oil is coming from another pool. And this process, which is the understanding of the hydrocarbon quantities from the different pools being commingled, is called production allocation. And production allocation, is fundamental for at least two reasons. The first one is for field management, because we want to know, the production performances of the different wells, of the different layers, of the different fields, let's say for internal use. But it's also important for fiscal reasons, because, the field, we might have fields, belonging to different operators, or, the fluids being commingled have different values and so on. So there are fiscal reasons behind it. So it's very important to perform production allocation. How do we do that? Well, there's plenty of methodologies in the industry. PLTs, test separator, multi-phase flow meters, and so on. I'm not gonna go through all of this in this presentation, but the takeaway message is, well, they are all expensive, still not flawless. So we're talking about geochemistry. So can we use geochemistry to address this topic, which is the production allocation? Well, let's go back to the previous example where we have two oils with distinguished fingerprints. Okay, so let's say they belong to separate compartments. Let's say they are produced together at some point. They're put in production and they are produced in a commingled manner. So can we use those differences, those molecular differences, to deconvolute, to mix the commingled oil in a quantitative way? Because what we need is a quantitative calculation. Of course, the answer is yes. And this is just an example, a scheme of how we do that. So let's say we are in this situation. We have sand 1 and sand 2 being produced together at the wellhead. Okay, so let's say that sand 1 oil has a fingerprint that is different from the fingerprint of sand 2. So we're gonna call these two pure oils end members. So every time we talk about end members, we're talking about an individual oil flow that will be at some point commingled. Okay, and when we talk about end members could be anything. In this case, two separate layers in the same well, but could be also two different oil flows from two different wells, producing, for example, from the same layer. Or it could be from two different fields. It depends on which scale are we looking at. So let's say we have sand 1 and sand 2 oils being distinguished through geochemical fingerprinting. When they're produced together, the resulting fluid, we always have a composition that we can think of in between those two. So if we plot the fingerprints in a radar plot like this one, the blue and the green stars being the two end members, the red star being a mixture of the two oils, will always be in between. And it is possible by deploying some math, some mixing algorithms to carry out the production allocation in a quantitative way. Of course, the process has a lot of advantages. It's a low cost, low HSE impact approach, because it requires just surface samples. It's not invasive, so no need for well intervention or production deferment, no mobilization or additional equipment. It's widely applicable, can be applied at any moment of the productive life of the wells, of the field. It's, irrespective of pressure, temperature, fluid type, and so on. Unless we are dealing with a very, very, very light oil, it can be applied very easily. And can be used for between fields, between wells, between layers, allocation, and it's independent of other allocation methodologies. So it can be used as a backup, as a validation, as a QC, as a calibration to other methodologies. But most importantly, it's a low cost technique, at least one order of magnitude lower than other available methodologies. But of course, everything is not just green. There are some, red points to take into account because there are limitations of the technique. And I put in bold the two most important limitations, in my opinion. So the first one, accuracy cannot be defined a priori. This means that it depends on how many M members we have to deconvolute and how similar the oils are. If we're dealing with, two different fields producing together, it's pretty easy to perform the deconvolution because probably very different oils and just two end members to deconvolute. But when we are dealing with many wells, for example, to be, allocated, well, things become more and more difficult. And also, another huge limitation is the end member absence. We need to fingerprint the end members first before doing the actual production allocation on commingled oil samples. So these are limitations that are pretty important, and we also need to understand first. To do so, we always, as I said, it's not a one-size-fits-all solution. But there are always some steps that we have to take in a rational way to ensure a successful work. So the first thing that we always have to do is define the scope of work. So we need to define which flows to allocate, to identify the sampling points, and to design sampling and analysis strategy. So this is something that is generally done in cooperation with the operator, okay? The second is what is called the feasibility phase, which I think is extremely important, where we collect and analyze the end member to see if we are actually able to distinguish them. We need to see the geochemical differences between the end members, and we also need to test the accuracy of the deconvolution. And this is normally done by creating artificial mixtures in the laboratory of end members and see if the system is able to accurately unmix these artificial mixtures. After that, we try to validate the mixing model that we just created. Okay, and to do this, we generally use some real production samples in a limited amount, and we try to compare the results with existing, if any, of course, production data, production allocation data, probably, for example, multi-phase flow meters data that are available, okay? And finally, after this validation is successful, upon, successful validation, we can move to an implementation phase where we adopt a routine sampling and analysis and reporting on a regular basis for years, ideally. And we put on a well surveillance and time-lapse production allocation plan to deploy for as much as needed. This is just an example taken from literature. And I like this example because this is the first time in which geochemical production allocation has been agreed between parties and accepted as the official methodology to provide fiscal measurements. And this is a case in the North Sea. In this case, 3 operators were involved. There was Total, there was Shell, and honestly, I don't remember which was the third one. But the takeaway message is still the same. They were using a mathematical process to understand the allocation. They had these 2 fields, Otter field and Eider field. Eider was the new field discovered, but at the time the price of the oil was very low, so they had to tie back Eider production to the Otter production. But Eider was producing much more than Otter, so and when they were doing the allocation by difference, they realized that the error in the Otter allocation was pretty high using this flow estimator. So they basically decided to move to geochemical production allocation as an alternative, more accurate way to do that. After an initial validation phase, which lasted for several weeks, they changed it. The flow estimator to geochemistry as official manner to understand, for fiscal reasons, the production. This is another case study that we carried out in our laboratory in cooperation with this company here, Wintershall DA, talking about a case study in offshore Norway. We've got this field, and we basically had 5 wells producing from the same reservoir. So we basically had 2 wells in the south, 1 well in the middle, and 2 wells in the north of the field. And as I said, this was a very, very, very complex case because we had 5 wells producing from the same formation. So a high number of N members to the convolute, very similar in terms of geochemistry. So that was pretty challenging. So 2 phases. First one was the N member characterization, and second was the test on the real production samples. Well, first phase seemed like it was pretty successful, like we were able to see the differences between the 5 wells on the field. And when we carried out allocation of real production samples and compared to the existing multi-phase flow meters data, which are the black dots in these histograms, well, we found an agreement that was not perfect for sure, except for the first sample, which was completely wrong. But the operator knew that they had some sampling issues, so they actually expected something was wrong. But anyway, in the other 4 samples, there was a pretty decent agreement. Was not perfect, but they also expected that because the flow meters were never calibrated. So they trusted flow meters, still not that much. So they wanted to have a backup or at least a second voice on this matter. We published this in at the SPWA conference this year. So if you're interested, you can check this out. But anyway, this also brought to the establishment on a monitoring programs for at least a few more years to come. So this is just an example of how we use geochemistry in production. Finally, I want to finish this presentation by just giving you some information on unconventional, how we use geochemistry in unconventional. Well, and in production in unconventional. Well, we're still talking about production allocation, okay? But when it comes down to unconventional, what happens? Well, in unconventional, we generally drill long horizontal drains, then we frack it, okay, so we stimulate the rock and we create a fracture network. So what we call the stimulated rock volume is the complex fracture network generated when a well is hydraulically fractured. After that, we pump some propellant into those fractures to maintain those fractures open. And later, what happens is that there is the drained rock volume, which is part of the stimulated rock volume that represents the fraction of the stimulated rock volume that actively produces oil. Okay, so when it comes down to unconventional, the operator always needs to answer 3 questions. Are we producing the oils from the zone we landed or from adjacent and geochemical distinct flow units? Because those fractures can go upwards and downwards in an uncontrolled manner. Okay. So is production consistent through time as both production stabilizes, field development progresses? This is very important to understand. And also for well spacing issues, has well spacing been optimized to maximize drainage from the landing zone? So this is the idea. But when it comes down to have end members, it's very difficult in unconventional because there's no well testing. Like we don't take these T samples or DT samples, for example. So the idea is try to get fingerprints from cuttings or from core samples and then carrying out production allocation to understand frac heights, frac drainage, evolution of those network over time, and so on. we due to time reasons, I cannot go into too much detail. I just reported here an example of one work that we did. We presented at URTEC a couple of years ago, where we also integrate production allocation through geochemistry tools with formation evaluation carried out using surface logging tools. It's a pretty comprehensive work that we did. So just, if you're interested, you can check this out to get more info on the applications in unconventional. So just to conclude, what I talked about is a cost-effective approach. Which helps us to understand subsurface structures and dynamics. And nowadays is a proven, mature technology, widely accepted. Is simple, widely applicable, and can be used to address many topics. Some of them I mentioned it, some of them I did not. Feel free to go through literature to have better insights. And finally, last but not least, it's not a one-size-fits-all approach. And it's not a black box approach either. We always have to evaluate the feasibility, limitations, and required approximations for all specific circumstances. And for sure, integration with other tools is key to success. Here I reported my contact, so if you're interested in something, you can reach out. I would be very glad. Thank you all for your attention, and please, if you have questions, feel free to ask. Thank you.
Thank you, Dr. Franco, for an excellent presentation. And at this time, we would like to open the floor for a brief question and answer session. So if you have any questions for Doctor, please feel free to raise your hand or submit them via the chat box.
Hello, thank you for this interesting presentation. I'd just like to ask if the oil sample itself is contaminated, is there a way to know that before starting the tests?
Well, yeah, for sure. Well, it's pretty, when you have a contamination, for example, from drilling additives like oil-based mud and everything, from the chromatograms, it's pretty easy to see that, because it's very, very clear when you have a contamination from drilling fluid. Said that, you can, for example, decide if contamination is limited to a specific part of the chromatogram, which you can decide to use a part of chromatogram, part of the fingerprint that is not contaminated by oil-based mud. And I showed you an example before, like, let me get back to this one. Okay, so in this case, we were dealing with cuttings. Okay, so we had OBM contamination, some OBM invasion. But as you can see here, the OBM invasion was very, very, very limited to this part of the chromatogram, as you can see. Because, when you have biodegradation, you can see all this part of the oil being eaten by the bacteria, but this part here is not touched. So we can easily see that this part of the chromatogram is just oil, OBM contamination, while from here on, we don't have any contamination. Okay, so we decided to use this area, outside the contamination to carry out our interpretation and all the study. So yes, of course, when contamination is always a big issue, when we deal with proper oil samples, this is generally not a problem because it's unlikely to have huge contamination. When we deal with carrier samples, this is generally the biggest problem that we have, and we also always have to take this into account. But as I said, it's pretty easy to see and to distinguish oil contamination or OBM mud contamination, from the chromatograms.
Thanks again.
You're welcome.
I have another question, Dr. Franco, related to the advanced geochemical analysis, such as diamondoid, QEDA, and the GCMSMS. how can this advanced tool help us in the identification and characterization of the conventional and unconventional resources?
For
Shell
that,
and deep reservoirs.
okay, so, okay, so when we talk about diamondoids, okay, they are generally used for a specific geochemistry interpretations. For example, diamondoids are particularly useful to understand multiple charges in a reservoir coming from low maturity and an high maturity source rock, for example. Okay, so in that case, we use diamondoids because behind the diamondoids there is a geochemical a geochemical meaning, okay? And this is very useful. The target here, and this is very useful in exploration. In this, in the applications that I showed you, using diamondoids, it can be done for sure, but in general, we can use any class of compounds as long as we use them to identify molecular features that are distinctive of that oil. In this case, we are not interested in evaluating maturity, for example. We are not interested in evaluating the multiple charges, for example, like diamondoids can help us to do that. But for sure, as I said at the beginning of the presentation, there is no a predefined methodology to use. We can use as which methodology we like most, as long as it will allow us to get reproducible information and consistent information from the oil. So one typical way to make a fingerprint of the oil could be running all the geochemical analysis, the standard geochemical analysis that we can run. So biomarker analysis on saturates, biomarker analysis on aromatics. We can run the diamondoid analysis using GCM-SMS. We can run standard high resolution GC analysis, light hydrocarbon analysis, and we can all put them together to carry out our interpretation. Of course, the way we treat the data will affect the kind of information we want to get. And for most reservoir geochemistry applications, we are not interested in the exploration meaning. We are interested just in seeing differences. The reason why we have those differences in many cases are not relevant, actually. I don't know if I answered your question.
Yeah, thank you so much. It's clear. So now after the question and answer session, I'd like to take this opportunity to express our gratitude to Dr. Franco for his enlightening presentation. Your expertise and insights have provided us with valuable knowledge in the field of the reservoir geochemistry. I would also like to extend our thanks, welcome, to the audience for their attendance today and their active participation. Once again, thank you, Dr. Franco, and thank you all for joining us today. See you soon in other events that will be organized by the EAGE local chapter of Kuwait. Thank you all.